Hello, everyone. My name's Andrew. Well, you probably already know that since you clicked the YouTube video. Anyway, I'm going to be diving into some questions that I've gotten this week, and then a overview of PK, PD, and biotransformation. Hopefully, brief video that'll dive into all these topics and help with my classmates' team-based learning project quiz thing that's tomorrow and our exam on Friday. So, we'll get straight into it with our first question. Get it up here. So, our first question was, are we responsible for knowing the list of inducers for each substrate? And this was something that I was going to ask Dr. Saressa tomorrow, but I just wanted to also give my point of view on the topic. So again, full question. Are we responsible for knowing the list of inducers for each substrate? I see our pharmacokinetic and pharmacodynamic and biotransformation, all these lectures, as more of like a 1,000-foot view kind of thing. So instead of perhaps knowing exact inducers, I would know, I would seek for understanding of these four things instead. So more like, what is induction and inhibition? What does that really mean? If something is induced or inhibited, how does that change an enzyme's activity? How do those changes alter a drug's concentration if that drug is metabolized by that enzyme? And then, if a concentration of a drug changes, what effect could there be on of the drug itself, or do you think there could potentially be toxicity if you were given like what the LD50 of a drug was? I think these are more important things to keep in mind rather than what specific inducers are a substrate. Like, let's do yellow. With induction, right? What can you reasonably expect when an enzyme is inducted or induced? So if an enzyme is induced, you're going to notice increased CYP enzyme expression, right? So there's going to be more, that enzyme's going to be more prevalent. It's going to be more present in the system. It's going to metabolize more. You're going to have increased metabolic capacity, either because that enzyme is more numerous or because that enzyme is more efficient, and so it's able to metabolize more. You're going to have, this is just a consequence of that, you're going to have faster drug metabolism. So let's say this is 3A4. If you've induced 3A4, all of a sudden you've now induced a major drug metabolizer in your body. So drugs are not going to be as efficacious if it's not a prodrug. And if it is a prodrug, you're going to have far more of it compared to before. You're going to have decreased plasma concentrations. This is what I was just talking about. You're going to have decreased plasma concentrations of parent drugs. So either that's a normal drug or a prodrug. You're going to have decreased amounts of that. If it is a prodrug, then you're going to have far more of normal drug because your CYP enzyme is metabolizing it quicker to its active form. If it is just a normal drug, then you're going to have decreased drug effect because it's being metabolized faster and it's not having a chance to be efficacious. You're going to have potential for therapeutic failure, potential therapeutic failure. And last but not least, for the prodrugs that I was talking about before, you're going to have this either increased prodrug or metabolite formation, or increased like prodrug to drug, increased prodrug to drug, and metabolite formation. I guess, let me actually mix that. You're just have increased metabolite formation, and it's important to know if that metabolite is active, an active metabolite, or if it's toxic. That's some things to keep in mind with induction and inducing CYP enzymes. So, inhibition is next. With inhibition, things to keep in mind, you're going to have decreased CYP enzyme activity. So decreased CYP enzyme activity, you're going to have slower drug metabolism. Slower drug metabolism. You're going to have increased plasma concentrations of parent drug. You're going to have potentially prolonged and exaggerated drug effects. Potentially increased risk of toxicity. That is not even English, I just wrote there. Increased risk of toxicity. And last but not least, decreased metabolite formation. So that's induction and inhibition. Those are like the big things, core concepts to know about those two things. And then the high yield enzymes. So the high yield CYP enzymes. I talked a little bit about these. I didn't talk about them. I actually wrote them in response to a question. I don't remember where, perhaps on the GroupMe. But I think the most important CYP enzymes to know, in my opinion, and also in my experience, are the 3A4, 2D6, and then 2C8, 9. I think these are the most prevalent ones to know. Okay, so this next question I got was asking, how does pharmacokinetic concepts apply to extended release or alternative release mechanisms and medications? And just here to say that all PK principles still apply. The only thing that's a key difference with extended release, or well, I'll just keep saying extended release because this is ultimately the same thing, is that extended release, only the absorption phase of ADME is modified. So what is ADME? Well, we talked a little bit about it, but it's absorption, distribution, metabolism, and excretion. Metab and excretion. So the main thing you're changing with extended release is your absorption part of ADME. Some things to know about each. I guess I'll talk a little bit about absorption itself. And this is mainly important in oral drugs. That's another thing I wanted to clarify. Diving into the differences between immediate release and extended release. So first things that I want to touch on are going to be immediate release. Immediate release versus extended release. So with immediate release, you're going to have rapid absorption, typically. Rapid absorption, you're going to have high Cmaxes. You're going to have large peak to trough fluctuations. So like your peak and trough values are going to have typically large values in between them, and you're going to have shorter durations. So these are more spiky. The graphs for these are going to be like be a little bit more like, and it goes down, right? There's a high Cmax, low Cmin. You get the picture with that first graph I drew. It's not quite so, it's not very smooth. Like it's like a big spike and then it goes down quick. Okay. With extended release, you have slower absorptions, lower Cmaxes, smaller peak to trough fluxes, fluctuations, more stable concentrations over time on average, more stable concentrations. You're going to have longer durations. And as a bonus, extended release typically over immediate release has improved adherence in patients. Because imagine this, right? With an immediate release formulation, let's say you need to take it 6 times a day. But with an extended release, you only have to take it once a day. It is extremely hard for people to remember to take medications if it's longer than 2 times or 3 times a day. It's very difficult to keep track of that. But if you just do it only once a day, then it's a lot simpler. We had like this small test that you could actually do in pharmacy school where if you got like, let's say you gave yourself 180 M&Ms and then you were asked to take the M&Ms at specific time periods throughout the day in order to simulate like as if you had a medication that was you were supposed to take 6 times a day. Almost every single person that did it failed, and the one person that actually was able to manage to do it did so because they had a alarm on their phone that would be constantly blaring at all times of the day for them to take it, which was quite a bit of a distractor in their daily life. But if you just take it 1 time a day, you're fine. As for the graph for these, typically it's going to be really like this, much more flattened and wider uh, compared to like our more spiky immediate release over here. Yeah. So the question was about one of the problems on the pharmacokinetics 2 PowerPoint. There was a half-life of a drug. So T1 half of a drug was 3 hours. I was told that the dose was 100 milligrams every 3 hours. The ratio between the concentration at 3 hours and the concentration at 0 was 0.5, which makes sense because half of the drug is gone at 3 hours because it has a half-life of 3 hours. And then I was asked, I'm just trying to double check here. Yes, yeah, so let's say we say the concentration at 0 was 100 mg per ml. And the question is asking for us to find asking for us to have a concentration at 3 hours of 100 mg per ml instead. I am drawing off the screen. Sorry about that. But anyway, 2.5, 3 hours, concentration at 0, 100 mg per ml. And the question itself is asking for us to solve for this. How could we possibly get a concentration at 3 hours of 100 mg per ml instead? So if I were to draw this out, then I would say this would be what it looks like, the graph. Here's 100. Here's 50. This is at time 3 hours. This is C3, and this is C0. So this doesn't work because concentration at 3 hours would be 50 milligrams per ml instead of the desired 100 milligrams per ml. So how would we get this value here? The ways to do it, you could either increase the dose of a drug, you could increase the half-life of the drug, or you could somehow inhibit the clearance of a drug. In the case for this problem, for us to get a concentration of 3 hours that's 100 milligrams per ml, the easiest way to do this would be just to double the dose. So instead of 100 milligrams, let's say we give 200 milligrams instead. So if we did 200 milligrams instead, doing the same graph, 200 milligrams per ml for the C0, we have our we have 100 milligrams per ml down here. This is our C3 new, C0 new, and this is at 3 hours. That's how we would get, this is how we would actually solve this parameter that they're asking of how do we get a concentration at 3 of 100 milligrams per ml. You just double the dose instead. Next thing that I'm going to do is dive into an overview of PK, PD, and biotransformation. Just a quick run through. I'll see you there. All right, everybody. So we're going to pick off here now with overview of PK. So what is PK? Well, we know that PK is the study of what the body does to the drug, as I explained in, like, I think one of my first videos. So PK is the study of like what a dose would look like as a plasma concentration versus time graph. Plasma concentration versus time graph. Some key parameters to know with PK, they're going to be your Cmax, your Cmin, concentration at steady state, your volume of distribution, your clearance, and your half-life. So Cmax, again, max concentration of a drug, minimum concentration of a drug. This is concentration at steady state, which is achieved in 4 to 5 half-lives. Achieved in 4 to 5 half-lives. Volume of distribution. Volume of distribution, which is how far a drug distributes into a body. This is particularly important if it's hydrophilic or lipophilic. Hydrophilic/lipophilic. A hydrophilic drug will have a lower volume of distribution compared to a lipophilic drug. A lipophilic drug would be able to infiltrate into more compartments in the body and would have a much higher volume of distribution compared to something that is more relegated to the blood. Clearance is the value of how do you get rid of a drug. So this could be this is mainly tied into your renal clearance and your hepatic clearance, which are your two main clearing drugs in the body, or two main clearing organs in the body, excuse me. And then this value changes if there's, most obvious example, if there's like some damage to like your kidneys or if damage to your liver. Your your T1 half, this is your half-life, and half-life is a determinant of like, you know, if in 50%, like how long does it take for 50% of a drug to be eliminated or metabolized or whatever. Okay, so those are some of our parameters, and we have actually some core equations to know as well for pharmacokinetics. I just learned about this today, so I wanted to add this to the PK part of this video. We have 4 equations that Dr. Hine highlighted as being of particular importance for us to memorize. So the first one that we have to memorize is the elimination rate constant equation, which is extremely simple, 0.693 divided by the half-life. And these two can be flipped around, so if you somehow got the elimination rate constant, you'd be able to calculate the half-life. That's equation 1. Next equation that we were requested to memorize is the equation where you can get the concentration at 0 of a drug if you take the dose of a drug and divide it by its volume of distribution. You'd be able to do shenanigans to this equation as well and rearrange it however you like to solve for dose and volume of distribution. Next, third equation is our clearance equation, where clearance equals the elimination rate constant multiplied by the volume of distribution, which also can be rearranged however you like. Then our fourth equation is a little bit of a bigger one, and it is our concentration at steady state equation, where you can take the bioavailability of F, multiply it by the dose. You put these in parentheses so you know they're different. Well, bioavailability F, the dose in D, divided by volume of distribution, multiplied by the elimination rate constant, and then by the dosing interval, which I'm going to put down as tau. Those are the 4 equations that I saw today, I think on the paper that I cannot remember who shared it. Let me double check here. Note updates. Michaela, my queen, she shared this doc, and at the very bottom it said a reminder that exam soft blah 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 blah. Each of the equations developed in terms of the course exam, it's recommended that the 4 equations below are the most important to memorize. So you actually do need to know them. Lovely. Anyway, these are the 4 equations written out here. And again, these can all be rearranged to solve for whatever you need. Okay, pharmacodynamics. So pharmacodynamics is the study of what the drug does to the body. So this is a lot of graphs that are like effect versus time. Like effect versus time graphs. Effect versus time. Some key terms to know: pharmacodynamics. This is a lot to do with receptors and agonists and antagonists. So what is an agonist? Agonist activates a receptor. An antagonist is something that'll block a receptor. We have partial agonists. Just make that all one word. Bad. Partial agonists, which activate receptors weakly. Activate receptors weakly. And then finally, we have something special. A little bonus, we have an inverse agonists, which reduce receptor activity. Reduce basal receptor activity. This one's just a bonus I wanted to add. A new type of agonist. The graphs for this, right? So the pharmacodynamic graphs, a lot of them are going to be something that look like this. It's going to have x-axis, which is going to have log drug concentration, and you're going to have a y-axis with effect. Maybe something like this. And double checking here. Some parameters to remember. Emax. Emax is maximal effect, maximal efficacy. Then you also have your EC50, which is how much concentration you need, how much drug concentration you need to get 50% of maximal effect. You were interpreting the graph again. I guess no. Let me add in another graph here. So let's say, all right. Let's say we have one drug that's like something like this. Okay, y'all. So we have a graph here with different kinds of parameters to keep in mind. So looking at this, we have different Emaxes and different EC50s for these drugs. I'm going to do this in red. So we can see here drugs A, B, and C. We draw some EC50s. Yeah, good enough. We could see that this is drug concentration again, y'all. Log drug concentration, and this is effect. So we could see that drug A has the highest effect out of A, B, and C, but it does only second best on how potent it is. Drug B is the most potent, which is determined by how far left the curve is. So you need less concentration of a drug to get an effect, but it does not necessarily have the same effect as drug A. And finally, we have drug C, our quote-unquote worst drug here, which is the least potent, so you need the highest drug concentration to get an effect, and it's also not as efficacious as drug A. This is how you can interpret these graphs, these pharmacodynamic graphs. So the more left it is on the graph, the more closer to zero it gets on the drug concentration log axis here. It means the more potent the drug is, and the higher it goes on the effect y-axis. Just as stated, it'll determine how efficacious that drug is. So, talking about some additional parameters. If you have a drug that's an agonist, so an agonist, its main effect is it wants to work on Emax. So it'll have increased Emax. If you have, let me get these out here. So I'm going to dive into this. Drew some graphs out for agonists plus competitive antagonists and irreversible antagonists. So we have here a just normal, let's say this is just normal agonist, yellow. The yellow is a normal agonist. If you had you add a competitive antagonist to just this normal agonist, then you would shift the dose, should have drawn these dose. You'd shift how much you need. Agonist plus competitive antagonist. You'd shift how much you need to the, you'd shift the graph to the right. So you would still be able to get the same kind of effect. Both your agonist plus competitive antagonist would still be able to reach the same Emax, but you would just need more drug, more concentration, or more dose, in other words, to reach the same Emax. That's agonist plus agonist and competitive antagonists. And then we have this graph here. The same thing, this is concentration and effect here. But this is now a drug. Mark this out so no one gets confused. This is now normal agonist. And then this is the agonist plus an irreversible antagonist or a non-competitive antagonist. So it's attacking at a different site. And what it's doing is the concentration is not necessarily, you don't necessarily need more of a drug to, it's not like up here with these ones where if you just add more concentration, you'll eventually get the same effect. With competitive or with non-competitive antagonists or irreversible antagonists, they are essentially lowering your Emax, and you just won't get the same kind of effect no matter how much drug is on board. Of note, if you added a partial agonist to this, a partial agonist would look extremely similar on this graph. A partial agonist plus a full agonist will make a graph that looks somewhat like this, where you just have all of a sudden less of an Emax because a partial agonist will have a smaller Emax compared to a full agonist. Clear some space here, move on to the next topic. All right, everyone. We're going to talk about, lastly, in pharmacodynamics, therapeutic index. The therapeutic index is a measure of how much of a drug you can give before you start to see toxic effects compared to like normal drug effects. So the higher your therapeutic index number is, the more leeway that you have with giving a drug before you start seeing toxic effects. I guess I could draw a little graph here as an example of what that would look like. So you have these therapeutic index, you'd have dose, milligrams down here. You'd have, say, percent of patients that show an effect. Make this 0 to 100, 200, 300. And then let's say 20, 30, we just want 50% really, that's the important one. Let's say 100's up here. So let's say to get the normal effect of a drug, it's something like this, where at 100 milligrams, this is effect, like good effect. At 100 milligrams, 50% of patients will have the desired effect of a drug. Then, let's say your toxic effect of a drug is toxic dose. At the toxic dose of a drug, 50% are here. I meant to make this 300, but let's say this is like 270. So here, at 270 milligrams, 50% of patients will show a toxic response. So they'll show a toxic side effect. Meanwhile, here, 50% of patients will show the desired effect of a drug. So what you would do is you take these two values. So you take your 270 milligrams for when 50% of patients will show a toxic response, and you divide it by the milligrams where 50% of patients showed the desired response, your ED. So just 270 divided by 100, and you'd get a therapeutic index of 2.7. This isn't terrible. But why is this important? It's because there are some drugs that have, especially chemotherapy agents, that have therapeutic indexes that are pretty much almost 1. So what does that tell you? Well, you will get an effect. That drug will have an effect, but at the same time that the drug has an effect, it is also producing a toxic response. This is always important to keep in mind. The higher your therapeutic index value is, the more leeway you get. But the lower it is, you need to be much more careful with caring for the patient and making sure that you're on top of managing adverse effects. This also has some utility with overdose in the case of like if a patient comes to you and tells you like I just swallowed an entire bottle of pills. If you know what kind of medication that is and you know the therapeutic index of it, if it has an obscenely high therapeutic index, then the patient may not have too severe adverse effects. But if it is a medication with a severely low therapeutic index, like a therapeutic index of 1.5, and they just told you they swallowed an entire bottle, then they are on track to easily hit the lethal dose. So you need to take action very quickly in that scenario. So, biotransformation. Biotransformation is what a body does. So, what body does to chemically modify. What body does to chemically modify drugs. Modify drugs to promote elimination. Promote elimination. So some important things to think about in biotransformation are like phase 1 and phase 2 reactions and your CYP enzymes. So with this is also like a metabolism phenomena. So what are some primary organs that you think of with this? So with biotransformation, first thing that comes to mind when I think about biotransformation is your liver. That's your major site of biotransformation. That is where your CYP enzymes are going to be. But there's lots of other places where you could potentially have biotransformation. But the main thing that I'm concerned about is our liver. So what is the reason for it? Well, you are working to increase a polarity of a drug. You're working to increase polarity of drugs because you want to make them more water soluble, increase water solubility ultimately, because you want to get them into your blood and into your kidneys to then be filtered out by renal excretion. So increasing your polarity of a drug, increasing the water solubility of a drug, enhancing renal elimination, and also biliary elimination. Forgot about that. Renal and biliary elimination. Sometimes in the liver, it is activating prodrugs. So you're sometimes activating prodrugs. Activating prodrug. And then occasionally, if it doesn't, if it's not a great compound that was ingested, sometimes you are generating toxic metabolites. Sometimes generating toxic metabolites. So then diving deeper into the reactions with phase 1 reactions. In phase 1, you are introducing or unmasking functional groups. So introduce or unmask functional groups in phase 1. Functional groups. So the main ways that this is done in phase 1 is through oxidation, reduction, or hydrolysis. This is a primary component of our CYP enzymes. Okay, and phase 1. And then phase 2, with phase 2 reactions. Phase 2 reactions, you're working to conjugate large polar endogenous molecules. So lots of different ways phase 2 reactions can happen. You could have glucuronidation. could have sulfation, acetylation, methylation, glutathione conjugation, glutathione conjugation, glycine conjugation. The results ultimately of all these phase 2 reactions is that they want to make highly polar compounds. Again, they make them polar because they want renal or biliary excretion to be enhanced. To be enhanced. Pretty rough and quick run through of PKPD biotransformation. Good luck to anyone on our TBL tomorrow, and good luck on Friday. If you ever have any questions, don't hesitate to reach out. Thank you, and see y'all later.